Thank you for that awesome introduction. So now I got to put on my serious face after the thumbs up. I wish there was the effects I could do, but unfortunately that doesn't exist on this stage. So just going to presenting on some research I've done, focusing on what the title is, collaborative multi-decision making via action suggestions. We're going to dig into each one of those terms in a second. But first, let's just start off with human decision making. So I had to change this because some of you have seen the slides before. But real quick, what's the answer to this question? Anybody right off the bat have an instinct? Maybe order of magnitude? 838,102,050. Like, you guys should be able to calculate? No, right? Like, that is something we naturally do. I memorized that number. Like, I didn't just do that. I'm not one of those people. There are some that exist, but it's not common. However, let's say you're driving down the road, you look out, you see a stoplight, and as you're coming to a stop, you see this. Probably haven't seen this example before. If you have, we probably need to talk about your driving habits. But this is an abnormal situation. But there's probably some gut instinct. Maybe it was a slam on the brakes. Maybe it was to counter steer into it if you had a defensive driving. But there's some natural reaction you had at this moment. Pretty robust. But the question was, how good is that decision? How good was the decision you just had as a gut instinct? There's a lot of evidence from some Nobel laureates like Kahneman and Tversky that talked about that human decision making fails in a lot of cases, thinking like the number calculation, probabilistic reasoning, et cetera. However, there are cases that you can, a lot of other research that the heuristic biases work has shown us that if we have problems that are time constrained, we can't really define the problem well, or we just don't have the data. We don't have the scientific evidence yet to suggest it. Those are times where humans can excel, and primarily expert humans can excel in these situations. So if we had to grade where we're at, I would say there's some categories that we clearly are not good at. There's other categories that, hey, we can do some pretty good decision making with an asterisk because not everybody's probably used to a car jumping across the curb. So maybe some expert aspects in this part. So human decision making, now let's focus on the computational side of things. So here's just a quick timeline where it goes to some highlights here. So prior to 97, we had like Connect 4 being solved. You should always go first, you'll win. Checkers, always a draw. So like those have been solved. 97, Deep Blue, Gary Kasparov. 2005, we were the first finishers of the DARPA Grand Challenge, and that's Stanley from Stanford. 2011, IBM Watson beat Ken Jennings and Brad Reuter. 2015 was when the convolutional neural network from Microsoft first surpassed human performance and the ability to identify images. 2016, Lisa et al. Lost AlphaGo in the game of Go, which many people didn't think was going to happen until years later. And then we start seeing this explosion of either poker, radiologists detecting lung cancer, AlphaFold, diplomacy with Cicero, and then we all are aware of what large language models are capable of. Maybe not fully yet, but some of the progress they're doing, which is phenomenal. The question is, like, what about other aspects of things? So this exact scenario here was, and somebody here probably may have been on Waymo at the time, was this particular result. So this was an accident in Phoenix down there right after they launched. And so there are certain cases where it just slowed down because it probably hasn't been trained on a car jumping across the curb at it, and the car ran right into it. If you actually watch the YouTube video, I will caveat of it would be a very difficult situation to avoid. So if we had this scale of where we could, there's some things that robots are clearly good at, and then there's other aspects that maybe there's some out of distribution stuff that's hard to capture everything. And again, I put an asterisk on that one because that was from 2018. There's been a lot of progress. I'm not saying Waymo is perfect yet, but there's been a lot of progress. But you could probably pick a lot of examples that insert a failure of a computational algorithm that is out of distribution primarily. So this research is focusing on how do we get the best of both? How do I combine the precision of this algorithmic decision making and the power of that with the creativity, ingenuity of human decision making and primarily human experts? And focusing on the how. How do we combine those two? So to motivate that example, or motivate the answer to that, or at least where my research is focused, let's think through a hypothetical situation. We have some earthquake that happens. As a result of this, we have infrastructure damage, communications is challenged, et cetera, collapsed buildings. And we're putting together a team to do some sort of search and rescue exercise. In this scenario, maybe we have a group of team members of 4 people. We have some notion of the map of the environment. We know where some dangers are. We know where some rubble is. But it's the real world, so it's partially observable. Like, not everybody can share stuff. It's a chaotic situation. We're trying to rescue survivors. So there's partial information. And then we have information that come in to the team leader that there's survivors on the eastern side. And he reaches out and tells his team to go check the stairwell on the western side. Wait a second. You just said survivors on the eastern. Why would you go to the western? The fact that this is an experienced team leader in a chaotic situation implies information like that decision is optimal from his perspective. He probably has knowledge that the western side is clear. Maybe he knows there's damage on the eastern side. So that information alone, that action suggestion, conveyed a lot more information than just those words alone of go to the western side to check it. And so we're going to focus on how we combine these idea of action suggestions in a collaborative environment, knowing we're all trying to achieve the same objective of rescuing the survivors in this multi-agent scenario to kind of make it more tractable in our decision making. Which leads into the primary insight, which is suggested actions contain a compressed signal about the belief of the person making it, assuming they are trying to be collaborative, optimal, et cetera. Which will lead to our primary 3 contributions. We're going to go through these quickly because we're going to spend a lot more time later on each one. First one is thinking like robot-robot situations or multi-agent teams of how we can reduce the number of potential beliefs that the other person has to reason over. And then how can we combine those beliefs then to form a more efficient decision making? The second contribution is focusing on more of like human to robot. So how can you provide a suggestion to a robot and it update its belief and maintain its own autonomy without you taking full control over it? And the third contribution is using that kind of framework to look at explainability, meaning if I had made a suggestion in this situation, what would have to change about the environment? And can I use insights from our knowledge of compressed belief signals to kind of infer of what the policy was actually doing in that case? But before we dig into each one of those contributions, we're going to start setting up some background. And if you're aware with Sizzle, you're probably aware that I'm going to set up MDPs, POMDPs, et cetera. So life is a POMDP. We're going to talk to it a little bit for those who aren't fully familiar. So let's say we have the search and rescue scenario. We have an autonomous robot and a survivor in this location. We can define this as a state. So we're talking about the calligraphic S defines the state of the world, where the survivor is, where the robot is, the XY position of it, where the hazards are, et cetera. That is the state. We can choose an action. So thinking our choice of actions are go left, right, declare the survivor found. And then we get rewards for certain actions in states. So if we find the survivor, you get a positive reward. If you decide to drive into a wall or drive into fire, like that's probably not a good thing. We want a negative reward associated with that, or you run out of battery. So there's our reward function. And now we decide to take an action and we progress to the next state. Unfortunately, the real world isn't deterministic. So there's some stochastic distribution of the next state you can go into, and that's our transition function. So what's the probability of going to the next state given I started in one state and took an action to get there? We go to the next state and we repeat this process again and again and again. And this is a Markov decision process. So if you represent this scenario as a dynamic decision network, and a Markov property is we only need to make decisions based on our current state. We don't remember the past. That's another key component there. However, Markov decision process assume the world is fully observable. But unfortunately, that isn't always the case. There's this partial observability aspect where you can't fully see where the survivors are. Otherwise, it wouldn't be search and rescue. It would just be rescue, right? So how can we extend this? We can extend this to a partial observable Markov decision process, or a POMDP. So instead of being able to see the world, we get some noisy observations. Maybe we can hear the survivor. Maybe you have a non-directional beacon they activated that gives us an indication of where they're going. And we can model this as a set of observations and the probability of receiving that observation given the state you transition to after the action took, our observation model. And we're not done there. So normally we end in POMDPs, but we're going to go on to multiple agents now. So not only one agent in the environment, now we have 2 more agents in the environment. So multiple agents. So each agent can take their independent actions, but we're collaborating together to try to maximize this reward. We're trying to find the survivors. So we can transform our POMDP into a decentralized POMDP or a DEC POMDP. The DEC part just means they're operating independently, and they receive independent observations in a shared environment and a shared reward. The goal of a DEC POMDP is to find a policy. Find something that maps my current belief or my states to the best action in order to maximize that reward over time. And that's what this term is looking at here. The discount factor just is a way to balance how much you value your immediate reward versus your far reward. And you can, based on the environment, tune that. So the question though is, how hard are these to solve? MDPs, so thinking like the team, so if you're not familiar with computational class complexities, here's a great image from Wikipedia, like on the right side, but this is just kind of for reference. Markov decision processes are P-complete, meaning we have polynomial time algorithms. Like, yeah, they're hard. Like the game of Go can be modeled as an MDP. It was very hard to solve, but yet it's polynomial time. And those are like the tractable categories of things. POMDPs go to P-space complete. So thinking exponentially hard in the worst case. So a lot of people will put them in the intractable category, but our lab likes to focus on with good modeling assumptions, you can actually get some really good policies out of them to help you make these informed decisions under uncertainty. DEC POMDPs, on the other hand, are in this NEXP category. You probably aren't working a lot in the NXP because it's doubly exponential in the worst case. Hasn't been proven yet, but a lot of evidence suggests that. But to kind of put it in perspective, this is the order of magnitude of policies that exist. It's a lot of symbols. So let's just go into a quick example. 2 agents, 100 states, so thinking like a 10 by 10 grid world, really simple. 4 actions, up, down, left, right, and only 5 observations. Up to a horizon of 2, it's 10 to the 7th policies. Horizon of 6, you're in this weird 10 to the 4703, very large number. And it's exponential to evaluate how good each policy is in the horizon with respect to the state and action space. So it's really hard. In comparison, the number of atoms in the observable universe is in the order of magnitude of 10 to the 80. So how can we take advantage of that? It leads into our first contribution. Is there a way we can use communication? And we're not the first people to think about that, because communicating is how we are advancing knowledge, et cetera, and sharing ideas. So if we had our group of agents and they had some communication network and they're talking back and forth, then we can take our DEC POM-DP and treat it as if it was a POM-DP. So we can plan centrally offline and then execute online, assuming we all have maintained the same belief. And the way to do that is we have to have 0 cost, so we can't charge this communication, and it has to be expressive enough to share the observation space. So that just allows us to maintain this joint belief. So when we're all executing with our own policy, we're all making the same actions together. So that's kind of where the theory behind leads us to. So if we can then plan as a POM-DP, so we're planning as a multi-agent POM-DP, we're back in the P space. A lot of work has shown in the past that POM-DP value function is piecewise linear and convex. The details of that aren't really important, but has led to algorithms that mean we can represent policies using alpha vectors. And this is an example we're going to use throughout to kind of motivate some of these ideas of in what the belief subspace looks like. So this would be an example of a policy for a POM-DP. So let's just walk through an example. So if my belief is 0.2, my joint belief is 0.2, I'm going to look and find the vector that is dominating in that belief space. In this case, it's a blue one. So it says I should take action 2. So I take action 2. I transition to a new state. I receive a new observation. I receive all the observations from all the other agents. I move to a different belief, and then I do the exact same thing. And if I look over on the y-axis, I can see what the value of following this policy over time is, an expected utility. So let's go back though to that point 2, because I said we're going to maintain a joint belief. What if we were just slightly off of that true belief? What if we had a belief that's close to it? When this B hat example here. What if I didn't have the true joint belief, but I could estimate closely to it? Well, if we look at what our value would be, we'd have a difference of value because we're taking the non-optimal action or the right action first based on the belief we should have. And as you can see, as this B hat gets closer to B, our value difference goes down a little bit. And so I'm doing a hand waving here. If you want to look at this, we can dig into it later. But this kind of gives you intuition that we could probably bound the difference in performance based on how close that belief is. And that's true because piecewise linear convex means it's Lipschitz continuous. And so we have this Lipschitz constant over here, which means I have the maximum or worst reward I could get, and the 1 minus gamma is just your infinite term. So how do I scale that if I took this best reward or worst reward for infinite time? And I can bound it by how close my belief is with the L1 norm there. So that leads us into an insight of, well, maybe I don't have to reconstruct the true joint belief. Maybe I could estimate the true joint belief and execute with bounded performance with a POM-DP policy. So instead of computing a DEC POM-DP, let me compute POM-DP and then estimate. So we're focusing on now of not only the messages we have to share. If I have suggested actions, is there a function I can find that gets me close enough to B that I can operate now with a POM-DP policy? So that allows us motivation of there could be a function we could find. Now let's look into the reachable beliefs we could possibly have. So in this example, 3 agents, 2 actions, 3 observations. What are possible reachable beliefs we could have? So agent 1 knows it's taking action 1, but has to reason over what if agent 2 and 3 took action 1, and agent 2 received 1 observation, another observation, or another observation. So there's 3 reachable beliefs just on 1 joint action with 3 observations for agent 2. Well, we have to consider now all possible joint actions that are existing, and all observations for agent 2, in this case, which give us 12 potential beliefs we have to reason over. And this is one of the reasons you can kind of see of why DEC POM-DPs are so hard, because I have to reason over their beliefs, and their belief to actually have the belief over my belief, and their belief, and you can kind of see how this can get doubly exponential. So just the number of reachable beliefs, you can kind of tell, grows pretty rapidly in time. But let's say agent 2 tells you that it thinks action 1 is the best action to take. OK, well, that just gives us some information. Because if we go back to our notional policy, if they tell me action 1 is the best action to take, I know they're operating in this subspace. I know immediately that their belief must fall within this subspace. So let's go back to our reachable beliefs. We get a message. All our messages in this presentation will be sigma. So this is a message from agent 2 to agent 1. Then we can just say, hey, based on the first reachable belief that we think agent 2 could have had, let me evaluate the policy or my surrogate policy for agent 2, and does it match the message? If it doesn't, their belief must not be there because that doesn't meet action 1. And we do this again, then we do this again for all of our beliefs, and it turns out evaluating policies, especially when you have an offline like an alpha vector, is really easy. You just take the dot product and see what overall vectors and what's the maximum value. So we go from 12 reachable beliefs now down to 2. In the worst case, we can't, and you can't prune, you still grow exponentially, but in practice with most policies, that information of what action you should take drastically reduces the subspace, which allows you to get rid a lot of these policies. So now we can, having to reason over all 12 of these, we only have to reason over 2 of them, and now we can take these 2 beliefs, combine it with our real belief, and then estimate a joint belief and select one from that idea. And that's the idea of the MCAS algorithm bounded in like we just need to get close enough. If you're interested in more of the details, reference the paper that's under view in the bottom, or we could talk about it afterwards, or I love talking about it, so any point really. So these are the results. Any questions? All right. I was told to never show slides like this, but let's just look at the. So we did it for a bunch of DEC-PON-DP problems in the literature. So you don't have to be familiar with one, but they're pretty simple because DEC-PON-DPs are solving them, and they're NEXP. We added qualifiers to add complexity to them because we're sharing information, meaning sharing action suggestions. This is just a upper bound on if we assume full observability in a POM-DP real world setting. That's not the case. This column goes back to our idea of can we just approximate the true belief. So the multi-agent POM-DP means everybody's sharing actions and observations. We maintain a joint belief. So that's our true upper bound in this world. The multi-agent POM-DP-C, that means instead of actually doing the true joint belief, I'm going to combine the beliefs through some estimated method called conflation. Conflation is just a way to combine 2 distributions. You can do it through mixed distributions or other ways, but trying to get the most information out of 2 separate distributions. And you can see here that in these cases, if the observation is independent, you basically approach the upper bound because you're having very accurate estimations of your joint belief. And there's only a couple instances where you're just slightly below performance, but still approaching that upper bound. If we compare that now to what would be if you're just acting independently, so this is just my highlight of cooperation and collaboration is good because we can always do better, meaning the rewards are going to go up. And then this aspect is the algorithm we just talked about. So this is we are pruning, and we're using some estimation to combine the joint beliefs again. And we can see that we do approach the upper bound, but we're not quite there. And that's to do with we can't prune perfectly. So these failures often combine with either the conflation aspect of it, or you weren't able to prune everything perfectly, and you had to select between your estimated joint beliefs. And so there's some future work on potential selections and how do you appropriately pick one. And that kind of wraps up the first contribution. As we're moving into the second one, I want to go back to our search and rescue. The team leader told us to check the stairwell on the western side. How do we reason over suggestions? If I say, well, we should go to this restaurant, when would I recommend that restaurant? Well, if I know somebody's gluten intolerant, I'm not going to pick that restaurant. If it's closed, I'm not going to suggest that one. So there's a lot of information. We kind of put ourselves in that situation to say, when would I recommend the western side? And kind of use that to infer based on your own experience of when that would happen. But let's say we're dealing with humans, we're actually telling a robot. If I tell a robot to go check the western side, it's like, great, I'm going to go check the western side. Or do we want it to maintain information we get to it by telling it that and update its own belief? So we can use a surrogate idea to say, instead of when would I, when would Pi, when would my policy recommend the western side? And we can kind of use that as a perspective now to form this likelihood function over when that could be happening by putting yourself in that perspective. So you're using that policy as a mapping now between a suggestion to your own belief space. There's been work done on this idea of combining human insights to make algorithms better. So there's an iterative planning process. The idea is you generate a plan offline, and you look and you're like, should have checked this green location over there. So I'm going to provide some feedback that you need to check that and change it, and then it replans. So thinking like adding constraints to an optimization problem. There's the idea of just directly modifying. So a robot is moving, and you move the arm to a coarse location and let it fine tune, or vice versa. You fine tune a control of it. There's intervening. And a key insight from Spencer in this paper, they talked about of anti-intervention, either positive or lack thereof is insight. Because if my Tesla's driving and I'm not taking control over it, that's probably should feedback that it's doing a decent job, at least not enough to scare me, right? But the moment I intervene it should probably use that intervention and learn from it. And then there's the idea of demonstration of or imitation learning. So trying to mimic the human or try to figure out insights from the human by watching them do something else and imitating either their reward policy or how their policy works. But some key limitations, you probably are initially thinking a lot of them don't assume partial observability. A lot of them define predefined human strategies or requires valuable human time to have these demonstrations. So if we want in this model of how we can incorporate these suggestions, and I'm trying to model it as if it's an observation. We got to think about what this observation function is. So this is just a normal Bayes update with a bunch of terms up there. I think people put math on slides like I'm right now, just be like, hey, look, I can do math. So first notation, T minus just means the previous time step. And we're in the Bayesian world, meaning we have an updated belief on the left side. And this is a history of our actions, history of the observations we have organically, and we can say all the history of the possible suggestions we just received. So in the Bayesian, we start with some prior. So this is our current belief of the world. And we have our likelihood model of receiving our own observations and this idea of the messages of the action suggestions. And this is based on the whole history. But because we're in a MDP or POMDP state, we can make some assumptions of the Markovian property and some independence, which allows us to transform this into a decision network that looks like this, where we just have sigma, or our message, only conditioned on the state prior to it. We can also draw an arrow from the action, but not required. And then our update becomes something like this. And you're probably like, well, I've seen that before, especially if I've been in Sizzle. This entire right side is what your normal Bayes filter update looks like, right? I have my current belief through a transition, how my belief changes, and I'm updating it by the likelihood of receiving that observation. So just repeat this process over and over again. The difference is this other term we're here, if we're saying like, hey, I still have to get this probability of receiving that suggestion based on the state. So how do we do that? That insight before of when would pi make that recommendation? So what if it's just exactly like me? What if it's exactly like pi? So it's perfectly rational operating as a POMDP. Well, okay, that could work. So you just say, it would recommend that action when I would, exactly. Well, it turns out humans aren't POMDPs, and humans are 100% rational. At least, unfortunately, I know I am not. I make some irrational decisions from time to time. Getting a Ph.D? No, I'm joking. And so we can kind of relax that assumption a little bit, and the idea of scaled rationality. So thinking about some tau percentage of the time, it's exactly like me, and the rest of the time it's just completely random, right? So that might be a little too, give humans a little more credit than that. Maybe we have this noisy rational model inspired by some work in like the 50s in psychology, and has been used a lot in shared autonomy recently. So this just says scaling rationality based on how good that decision is. So thinking 0 is completely random, like don't trust that suggester, they're random. Infinity means they're perfectly rational just like you, going back up to exactly like pi. So let's look at what this, if we model it this way, what does this look like visually? So this is a tag problem from the POMDP literature. So you are the orange robot. This is your belief over where you think the other robot is, but you don't know where the robot is. You only know if it's in the exact same grid as you. But the one thing you do know is it moves away from you stochastically. So a natural policy would be I'm going to trap it in the corners, right? If it's moving away, let me trap it in a corner and go to the corner and see if it's there, if it moved away or not, and check the other corners. So if we watch how this belief will progress, you can kind of see it will go towards the corners. Let's say you're watching this agent, though, and you get indications of some noisy observation or somebody told you of like, hey, I think there's something on the western side there, and you want it to go west. Well, we can then transform this and check the western side into the action suggestion of, hey, move west. I think you should go west instead of the north or the east there. So there's a couple ways we can do that. We can just naively follow that path. If we naively follow that, we're not going to update our belief. We're just going to keep our belief the same. We're going to check our policy. Our policy says, well, my policy says I should go north, but team leader says I should go west, so okay, I'm just going to go west, and then I'll move on with my life. Noisy agent, we can actually update our belief based on this observation model, and we can kind of see this shift of probability mass to the west now. And a key aspect about this is you're not saying always go 100% to the west, because sometimes team leaders can be wrong, unfortunately. So you want to maintain some autonomy of just, I don't fully believe you, and you can scale lambda to change how much you want that shift to happen. In this case, it would look up its own policy, maintain autonomy, and it said it should go west. So we make that transition, and then we continue then octing autonomously after that one suggestion. And if we watch this, we can kind of see the naive agent now is just going to, great, you told me to go west, but now I'm just going to go back to what I think is right because you're not watching me anymore. Versus a noisy agent was able to imply, get more of that information, update its belief, assuming they're acting optimally, and then be autonomous towards the western side after that. So how does this scale? How good are we as far as efficiency, robustness? You can kind of see that there's probably some efficiency. When you give good suggestions, you're getting more information as we're able to shift some of our probability mass there. So this is, again, the tag domain across multiple runs. The top line is you know exactly where it is, so thinking MDP setting, so just how do you get the closest path. The bottom line is a normal POMDP setting, so you're receiving no observations, just acting as a POMDP. If you're naively following suggestions, the x-axis is the message reception rate. Thinking I'm giving them suggestions 100% of the time versus 0%. So you would expect, like, if you're naively following, you can approach perfection if they're always giving you suggestions. And the suggester model in this case is a perfect suggester, so they have full observability of the world. And then for our scaled and noisy agents here, we can kind of see this jump right there in the beginning. So when we're 100% receiving messages, they're all about the same. Naively following is not any better but that requires you to meet with your advisor every single day and then tell you what research to do that day. Probably not realistic, because most advisors are pretty busy, and so you might only get a couple suggestions every now and then. You want to maximize that amount of information, and we kind of see this efficiency growth in that smaller reception rate. So efficiently, okay, so that's great. What about robustness though? What if sometimes the suggester is not great? Well, that's where we see, so now we have a completely random agent on the bottom down here. So sometimes it finds it, or we'd run out of time. So if you're naively following a random suggester, you're going to be random. That makes sense. And then we can relax that assumption and say, what if I only follow randomness 25% of the time? And we can do something similar with those other parameters. Like I can change tau, I can change lambda in my model based on how much I trust that suggester. Well, let's just focus in on the left and right part here. So if my suggestions are completely random, I want to have a low value of trust. If my suggestions are perfect, I want to have a high value of trust. So like, wow, Dylan, like how do you determine what level? Like you set that off the bat and then you just got to hope that you're good at that moment. Well, luckily we can adapt that, and that's what we're going to lead into. So sometimes your advisor is not great, but you want to follow them. Luckily, I am in not that case. I'm in this other side over here where if my advisor gives me information, I want to follow what he says, and every little nugget of information I want to integrate into my belief space. Then there's the other people where they talk to you and you're like, that was fun conversation, I'm going to ignore what you said. And so we could put those associated with a lambda value here by how much we trust them. So in this case, we could be completely rational to, I don't want to trust this person at all, and that will give us a possible, in this case, we can model them as discrete settings of different suggesters. And we can take that now and augment our state space by this, our original state space with all the potential suggesters we have. And now when you receive your observations, you update either suggestion or your organic observation in the environment. If you told me to go west, but I tagged them on the east side, you naturally learn the quality of the suggester over time. So focusing in on, we did it across, again, just using this tag domain. We're thinking naive of how much I trust. So as naive value goes down, you trust them less. As the noisy value goes down, you trust them less. Versus the bottom is we're going to model a series of from 0 to 10 of how much you trust that agent. You can dynamically adapt. The TP equals 0 to 0.5. 0 just means I assume the suggester quality doesn't change throughout time. 0.5 is a way to dynamically change it. We're not going to go details on that, but reference the paper if you guys want more details or ask me afterwards. So the columns here are just what we're modeling the suggester as. So we're modeling a really rational suggester of 5.0 versus a medium suggester at 1.0. And if we kind of look into the certain columns here, so when the suggester is like okay, you would expect if you had the model accurate, the 1.0 value matches what you would expect. But as we progress, we see that whatever model is performing best changes, but we match their performance on the bottom, so we're able to actually learn the quality of suggester throughout the time, assuming it's static. What if it's dynamic though? What if throughout time, and this is 100 different trials of playing tag, what if the quality of suggester changes? What if they start off good but then go bad because they got distracted? So if you have a static model, you assume either lambda 5 or lambda 1. When the suggestions are good, green's above blue. That's great. You want to integrate there. But when the suggestions are bad, you want blues above green. So you want the lambda value of 1. If we dynamically adapt, based on modeling it by an augmented state space, we can kind of see that we're maintaining the trends over here on the left side. We're approaching the green, we're approaching the blue when we want to. But we notice this little trend over here on the right side of once we find out the suggester is completely random, all our probability goes there, and because we're not modeling the suggesters can change, it's really hard to get back to trust level when we should be trusting it. So you can augment that a little bit by modeling the fact that suggester quality can change, either becoming uniformly random or by certain state events of like, oh, I just got a swap out of somebody else providing suggestions. Maybe I should reset my distribution. And that's what the pink line example of is. So in this next contribution is focusing on the idea of explainability. And so it's a little bit different than what we kind of talked about before with suggestions, but I want to put it in the perspective of you would have provided a suggestion and how do you get information out of that when it didn't do what you thought it should do. And so our search and rescue problem, can you continue with the trend of POM-DPs? Let's model it as a POM-DP in a very simple scenario to let us visualize and kind of get insights into this problem a little more. So in this particular example, you have a home location where you have to return the charge, and you have some battery. So you can only go 20 time steps before you run out of battery, and you can go back home, and as long as you're at home and you say you want to charge, you'll go back up to 20, and you continue your search after that. We have some attraction points. So thinking like a survivor search and rescue scenario where you know there's water sources or you know there's food sources, they're going to naturally gravitate towards them. But like if it's an injured hiker, or they're probably not going to be able to 100% go there. So some probably distribution of moving towards those attraction sources. And then the reward scenario is you get a positive reward for finding the survivor. So you can declare the survivor found, and if it's in the same grid as you, positive reward because you're telling people to go there. However, if you declare the survivor found and it's not in the same grid, like that is a high negative reward because you just waste a lot of resources. If you run out of battery, that's not good because drones are pretty expensive most of the time. Some drones. And then your observations of you have an accurate but not very sensitive observation of your own grid cell. So thinking like I'm trying to see through shrubbery and brush. When I see something, I'm pretty confident it's there, but not 100%. And then a very noisy observation of further distance out. So within one grid cell is kind of how this simple problem works here. So we can start off with some belief. This was actually after the agent has already did one lap around and came back home and decided to charge. This is the next route out. And let's say we're watching it. We see it kind of search. We see it go up. It's going back down to the south. It checks an attraction point. It's coming home. And then you see, whoa, you have a spike of probability there. I'm not showing the observations for clarity, but it actually received a positive hit that it had a positive observation in grid 8. And then when it moved to grid 4, and that next time spot, it actually said it found I think I saw the survivor again behind me. So you have this sequence where it has a detection, has another detection, but it's like, I'm going home. I got a charge. I got a negative reward for going home. So the question is like, why? What would it take for it to turn around? So luckily, there's previous work we can look at to say, well, how do we explain this policy? Well, one option is let's just change rewards. Let's just move the rewards of running out of battery lower and find the survivor higher. So maybe you'll take more risk to run out of battery to declare it found. Or maybe let's lower the cost of false declaration. So that's the idea of like changing stuff based on rewards there. There's model reconciliation. Maybe you want it to be just like you and make the parameters of like, I would have declared it this way. So then over time, based on certain demonstrations, you could change your parameters of your model to be more like what you would have done. That's reconciling the model to be more in the align with what you expected. Then there's the idea of just, it's called sequential information probing in this paper. And so it's if I would have revealed the survivor being there, would you have done it? And the answer is like, yeah, like that would have been valuable information to have. But the question and the key limitation here is, a lot of them really haven't talked about the agent's belief space, which is fundamental in this idea of partial observability. So why can't we use that as a way to explain of what's the shift or change in belief space we can make happen to make that suggested action be the thing that it did? And that leads us into counterfactual. So counterfactual is like if we look at this example we just had before, we ask the question of when would it have declared found? Or the other one of when it had the second detection of saying, when would it have turned around and said, screw my battery, I'm going to try to find the survivor and declare it found because I have high confidence that it's there. Well, we can frame that from what's the closest belief that would need to exist for that action to be optimal? So if we go back to our alpha vector policy example, if somebody tells me that that they think a certain, so if my belief is 0.2 and they come through and they say what would have taken for action 1 to be best, we know it has to be in the subspace. So I can frame this as, given my current belief B, what's the closest belief in that subspace that would exist? Or what's all the potential closest ones if there's multiple subspaces? So luckily there's math tools. We can just frame this as an optimization problem. Let's minimize some distance between the beliefs subject to it must be in that subspace. And if we now then make the assumption, or we kind of like as an example, use an alpha vector policy. So this gamma just means a set of alpha vectors. This is going to change based on your policy representation. And we've also shown that you can do this for online algorithms, but just for simplicity, we're going to do it for an alpha vector. So we have a set of alpha vectors. This term over here on the right just says this is over all possible alpha vectors that are dominant. So in this case, just all the red ones. So again, we're trying to just more exactly define this belief subspace. And then so the term will eventually look like this. So what does this mean? We'll basically have my set of all alpha vectors associated with action 1, all red alpha vectors. This term just means when those alpha vectors are dominant. So between 0 and 0.1 and 0.7 and 0.8. So our optimization problem then looks like this. So what does that mean? Well, we have to make sure our belief is reasonable. So greater than 0 sums to 1, so a proper belief vector. We can now have a number of optimization problems. We have to do it for every subspace that exists, so in this case 2. And our number of linear constraints is every other alpha vector that exists that isn't associated with that. So in this case 4. So you can kind of imagine, like, as your alpha vector policies scale to thousands and thousands, that grows pretty rapidly, but a good thing is at least they're linear constraints. And now our distance, this objective function here, will help us dictate the complexity of how hard that problem is to solve. We have the L2 norm squared, it's convex. If we use like a Wasserstein metric or an L1 norm, we can frame it as a linear program, pure linear program, which are pretty easy to solve. Other caveats I would say on the distance function, it's going to be specific to the problem at hand, whether you're using the Kolberg-Lieber divergence for certain insights or maybe the Wasserstein in the search and rescue example, because you want to tie the movement of mass with how far that survivor could be away, which is what we use in our example we're getting ready to show. So now we can look at this problem, ask that same question, put it through our optimization problem and say, what would the belief be that would be closest in this Wasserstein space? And it turns out and says, hey, if the belief would have been 85%, I would have declared it found because it would have been worth my risk. So kind of very similar to the reward shaping, but from a belief perspective, what would need to change in your belief? But then you might ask, well, wait a second, this would make a declared report found, but that's on the boundary of your policy. If you know the alpha vector policy there, that's right where the red touches something else. So is that belief even reasonable though? Because most of the time in these planning spaces, you only plan over certain beliefs. So is this even realistic based on the series of actions and observations that could have existed to the robot? Well, we can, luckily math has helped us again, where we can just add constraints to say, well, be consistent then with the history of things we've seen and the policy. So not only what we've seen, but I still want you to take those actions up to that point. So if I move your belief around and I say it's a 100% chance the survivor is there, once you go to that location, you're going to declare found. So that wouldn't align with the observation sequence we saw where it had to do that path and come back home. So our problem ends up looking with an augmentation of the history. So we have a series of histories of actions and observations we've seen throughout time t. And we can shape it to look something like this in the abstract sense. So what are these terms here? Well, we have, instead of looking over the current belief, we want to start with a belief. So let's just look at how we can manipulate the initial belief subject to that trajectory history. So we're trying to find the closest initial belief. And these constraints say tau means how does my update function? How does my belief evolve? And you want to subject that to the constraint that the belief is going to evolve based on what you've seen, based on what action you took and what observation you received. In our example we've been doing, tau is just your Bayes filter, your Bayes rule kind of update there. This just says your policy has to be policy consistent. So you still have to be optimally following your suggested action up until that last moment where we put in a constraint that says your new belief must fall in this subspace of A1. You must declare A1 at that end or declare found. So if I wave a magic wand, we can turn this into an optimization program that looks like this. The details aren't really important, but I want to focus on a couple things here. Going back, remember we had this set of multiple optimization problems we have to solve because we have to look at each subspace? Well, that's pretty hard if we have to look for multiple optimization problems at multiple constraints. So we can rewrite that as a mixed integer program to say, is that alpha vector dominant or not? So that was one of the key enablers. And so these constraints right here are just saying you have to fall within that subspace at that given time. And this becomes a mixed integer program with binary variables. And so the number of binary variables we have is the number of alpha vectors associated with that action across time. So you can kind of little in the back of your brain going, integer programs are NP hard. I have multiple time steps. Like this could be a pretty hard problem to solve. Luckily, there's commercial solvers that are good, but that is definitely a limitation. So if we then do the exact same scenario, so this is what the initial belief was when we started, and this is where we got on the way back home. We can run that through our optimization program. In this case, I use Gurobi, and we get a solution out. So we get something very similar here on the right side, where you still get the 86%, but you see it different in the distribution of the probability mass. So you still see them more consistent with your initial belief, which, because you didn't ever search down there, why would you expect it to go to 0? But if we focus in on just this little section here, this is how our initial belief changed. So just slight changes. If you just barely increase the probability the survivor was in that location in or around that square to 4% or less, you have a change in policy and it would have declared it found on the way home. So now we can combine that with ideas like, could I have given a suggestion? What other sensor could I have augmented it with? Maybe I was too confident on its first couple passes that it didn't. So give us insight into how I can change either the design of the problem or, oh, that makes sense. It was very confident it wasn't there, so it didn't declare it found. So it wraps up the primary 3 contributions, but as most research, I talked about all the positives of it, but there's obviously clear limitations, right? Like nothing is perfect. In a lot of examples we saw, they're very toy problems, some computational challenges, et cetera. So right off the bat is there's computational issues here. So on the left side, we're still solving a POMDP policy, and POMDPs grow exponentially in complexity as a number of agents. So if I have multi-agent POMDP, that grows exponentially hard to solve in the number of agents. So like, that's an initial issue there. But can we do online algorithms and other ways to adapt it, take advantage of the problem? On the right side here, I talked about that mixed integer program. So you can quickly see that might not scale. What if we can't find a solution? Is there a heuristic we can warm start stuff with? So some clear limitations at that part. Another one is I made some really strong assumptions. I assumed people were acting rationally. On the left side, I assumed I had a perfect model. I assumed communication was perfectly shared between them to be able to prune those aspects of things. I assumed humans were operating in a scaled rational model. And there's a lot of evidence to suggest that maybe that isn't the best way to model human decision making. So when those assumptions start breaking down, we start seeing some failures. And then limited experimental validation. That's going to lead into some future work. So I was motivated, and I talked about human AI collaboration, but you guys didn't see any human studies up here. Like, wait a second, Dylan. Like, why did you motivate that? Because work on one, it's easier to not do an IRB. But joking aside, it's setting up the foundation to go into this. And I would say the initial future work is human-centered validation. I think is one of the first things that can go. And how does this fail or extend better when we actually integrate humans into this process? Can we combine the idea of suggestion and explainability? I kind of hinted at the end of, is there a way now that if I have a person monitoring multiple drones, is there a way I could use this explainability mindset to say, hey, you should provide a suggestion here versus just asking for a suggestion? And then the other one I want to highlight is multimodal form of communication. As you can tell, like, I gesture and move around a lot. I'm a very expressive person when I give talks. There's hopefully a lot of information when I'm emphasizing with my hands. And we as humans communicate a lot through gestures and multi-modes other than just talking. So how can we integrate that? Can we infer the suggestion and then do the same process beyond that? Which hopefully will lead us into this idea of like bridging expert intuition with the precision and computational power of algorithms. So when you tell a drone to go check the western side, it can maintain its own autonomy, reason probabilistically in its space it's really good at, but provide the suggestions and beliefs that we naturally have as humans based on our experience, even though it may not be perfect. And hopefully we can get to a day where we're more in this like integrated, shared joint decision making, capitalizing on each other's kind of benefits there. So that wraps up my formal part of the presentation, and I'll open it up to any questions or comments before the closed session.